On the screen, a homemade bandsaw facing a brutal sledgehammer test. But this isn't just about destruction. It's a story of how a simple machine, once tipped on its side, becomes a small sawmill, turning raw logs into beautiful boards. Along the way, I will share a few thoughts on finding and preparing your own one-of-a-kind woodworking timber. You've probably never seen such colors and grain patterns before, but that's just the prelude. The real story lies ahead. You will see 3 experiments sharpening a saw blade under makeshift conditions. I tried 3 different tooth geometries. All of my store-bought blades were welded crooked, so I straightened both the back and the teeth and achieved perfect blade geometry using improvised methods. Now I'm sharing that experience. Originally, though, this video was meant to be about a unique homemade machine whose frame is a blend of metal and wood, an extremely cheap composite material with surprising properties. You can't break its cantilever frame even with a sledgehammer. Following my example, you too can fit a sawmill blade onto your bandsaw, tip it on its side, and cut logs into boards of the desired size and length, while avoiding the mistakes and hidden pitfalls I'll tell you about in this video. As you may have noticed, I readily use my mobile tool cabinets as supports for my assembly workbench. On them, I've laid out the parts for building a plywood bandsaw. Using the saw frame as an example, I decided to test my idea of increasing the stiffness of plywood beam by integrating a sheet of metal into the plywood layers. To clamp the plywood sheets together, I used screws. Please note the deflection of the plywood part without the metal sheet. According to the reference data, adding a 1 mm steel sheet to one side of the plywood should only increase its rigidity by about 15%. But look at the deflection curve of the laminated plywood sheet. The deflection decreased by an order of magnitude. And what if you add 2 such sheets of steel to the structure? However, structural stiffness isn't the main point here. The key thing is the AFR, the amplitude frequency response. Even the reference data shows that vibrations in such a composite will damp out extremely quickly. That means there will be no vibrations in the machine. It will cut cleanly and almost silently. I will only hint that I was inspired by the design of a kinetic hammer. If you sand the edges smooth, you will get a pretty neat looking machine. A nice shot should be dynamic. But I wanted even more dynamics, and that's when things took a turn. The better is the enemy of the good. Here's a good place for comments. A pleasant dent. I lost my enthusiasm, and what's the point of doing something without desire? 2 years passed. I made peace with the failure and decided to patch the dent in the simplest way possible. I milled the crushed corner at an angle, prepared the patch from a scrap plywood, reinforced the corner with a screw, and glued the patch in place with wood glue. This repair method doesn't hide the seam between the patch and the saw body, but if you don't look too closely, it's fine. I saw off all the excess with a Japanese kataba handsaw and sanded the cut smooth. Now I can test fit the pulleys and see how the saw blade holds up on them in motion. The lower pulley is fixed in the body using this wooden block. The tension of the saw blade will literally try to tear this block out of the body, so it needs to be secured as firmly as possible. And that must be done before installing the lower crossbar of the saw frame, since it will block access to the part later. In this case, the sequence of steps is important. Now a steel axle needs to be installed into the wooden block. This is the shaft on which the pulley will rotate. The block already has a hole drilled for the axle, but its diameter is deliberately larger than the shaft. So to make it fit tightly, you should wrap a suitable amount of paper around the axle. Of course, by choosing the right amount of paper, you could also hammer the axle into place with a mallet, but that didn't work out for me. Fortunately, there is a thread hole at the end of the shaft. By screwing a bolt into the thread, you can pull the shaft into the hole effortlessly and with guaranteed precision. If you use a sledgehammer, you might drive the shaft in deeper than necessary. By inserting thin yellow strips of cardboard under the upper part of the block, you can fine-tune the tilt angle of the lower fixed pulley's axis. The tension blade will inevitably bend the shaft within the mounting hole, eliminate any play where the block attaches to the frame, and even flex the frame of the bandsaw itself. That's why it makes sense to install the block at a slight angle to the frame at the outset. Don't worry, once the saw starts running, all the play will settle out and the shaft will align perfectly perpendicular to the frame. To prevent the saw blade and pulley from pulling off the shaft under load, it needs to be secured with a washer. You can easily guess that I could resist turning custom-shaped washers. As you can see, I aligned the pulleys and therefore the saw blade with excessive precision. The lower pulley is now installed, which means I can finally assemble the frame completely and glue its base together. Since the entire frame is laminated with sheet metal, the base should be reinforced the same way. It's not good when the foundation itself is the weakest part of a structure. So I cut 2 strips of sheet metal, sandwiched them together with plywood strips, and glued the plywood to the metal. I cut the missing plywood pieces on my homemade miter saw and began assembling everything. Before gluing, you should always do a dry fit. As the old woodworking wisdom says, measure 7 times and glue once. My experience has shown that polyurethane glue bonds plywood to galvanized sheet metal rather poorly. Under impact, it peels off easily. To keep the technique clean but to improve adhesion, I sanded and degreased the metal surface. Where plywood joins plywood, I use regular wood glue. It has a longer open time. As you can see, in woodworking, it's not the size of the parts that matters, but their number and curvature. I spent about as much time gluing the frame base as I did on the rest of the frame combined. It's the small tasks that eat up most of the time, and that's exactly what lies ahead. To keep the project from becoming tedious, I decided to get the machine running as soon as possible. Tests and experiments are always more exciting than fiddling with small parts. My simple homemade guide rail, made from a square aluminum tube, is still in service. I actually use my DIY tools. They are not for content, but for real work. Notice that when I broke off the sawn section of the support, there was no delimitation between the glued plywood and sheet metal layers. That's encouraging. But next time I glue plywood to sheet metal, I will use a contact adhesive instead. The 3M77 aerosol adhesive performed better for this task, but if you can suggest even more suitable glue, I would appreciate it. Drilling the perpendicular mounting holes for the saw support frame by hand is easiest if you use a small prism as a guide. And with that, the saw's frame is finally complete. Now it's time to install the motor. I had a leftover off-cut of plywood, and with a bit of sanding, it will serve just fine as a base for the motor. For mounting and belt tensioning, I choose a pendulum-style suspension. That means I'll need at least 2 rails and a pivot shaft. The pivot itself will be a simple M8 threaded rod. I prefer to mark my measurements directly by eye on the spot. Once I've set the motor loosely on its platform, mounted on the saw frame, I can take precise measurements from there. Using those dimensions, I will drill a matching hole for the pivot right through the frame and the platform together. It's a deep hole, and I drilled it by hand, so I went from both sides, checking alignment with the prism to keep it square. Then I test fit the rod, measured its final length right there on the bench and cut it. Since I picked up a small metal cutting bandsaw, I hardly ever make dust in the shop with the grinder anymore. Now I will need to rip some plywood into narrow slats. That's easiest done with the slat on my homemade microformat saw. Though that means I'll need to make space for it down in the basement. And since I'll be using the bandsaw here in the main shop after setup, I should move the lathe off the middle of my workbench. On my temporary test stand, the motor doesn't quite fit, but that's fine. Using it as a guide, I can now mark the minimal footprint for the actual platform and the bolt holes for mounting. Once the layout marked, I trim the excess. When the slat is dialed in and cuts at a perfect 90 degrees, Working on the microformat saw is a real pleasure. This saw has stood up to years of work, and if there is interest in comments, I'll put together a full video on how I build it, along with a few accessories for plunge saw and the factory rails. Then, by accident, I discovered how handy a simple marking gauge is for transferring measurements from one part to another. Highly recommended that trick. The motor will be mounted with the furniture bolts, so I will need shallow recesses for their heads. Normally, I'd use 14 bit for that, but good ones are absurdly expensive, so I simply reground a cheap bit instead. All that's really needed is to grind the scoring knives, and it performs perfectly well. After about a month of tweaks and modifications, this piece of plywood will be full of holes anyway, but for now the goal is simple: mount the motor and do a first test run. So the belt is on, the power is connected, and right away you can see it, the motor isn't standing still, it's dancing. If I wedge a shim between the frame and the motor housing, things improve slightly, but that's just a symptom fix. The real cause? And run out on the drive pulley. The proper way to fix that is to true the pulley directly on the shaft, but I will admit, I took the lazy route, slipped a few paper shims under the pulley hub instead. At the same time, I nudged the motor slightly on its platform to align its drive pulley exactly with the driven pulley on the saw. Didn't nail it on the first try. Alignment is always a bit finicky. Clearly, it's time to add a pair of stiffening ribs under the motor mount. The motor is seated and we are ready for the first test run. Everything spins smoothly. I can cut, though for now only narrow stock. But my real goal is logs, which means I'll need proper blade guides. That's simple enough. First I will rip an 18mm plywood strip. This will serve as the movable arm holding the upper guide. Then I will cut 3 rectangulars from 15mm plywood. Those will form the housing the arms slides in. For assembling that housing, I decided to use a threaded rod. While drilling, I managed to snap my long bit inside the hole. It took me a moment to realize where the rest of it went. Extracted the broken piece and mourned the loss. Those extra long bits aren't easy to replace. I widened the hole with a larger bit and also drilled a path through in one wall of the housing. Cut 2 short lengths from the threaded rod, tapped them in, and used their marks to locate the matching exit holes. Under each washer and nut I made a small counter bore with a Forstner bit. Sure, I could have just screwed the side walls together with 4 regular screws, faster and easier. But remember the dent in the corner of the frame? If the frame takes another fall, those screws will not hold. Bolted joints just might. But I'd rather not test that theory. Now for the front wall of the housing. That one I'll fasten with screws after pre-drilling with my favorite DMAR countersink bit. And now, time to test my freshly ground homemade drill bit. Notice how it cuts, cleanly and no tear-outs. You can buy precise ground bits like that, but they are overpriced and rarely stocked in all diameters. Personally, I prefer to reshape a high-speed steel bit for each task. Meanwhile, I have pressed in a T-nut for the clamping screw that locks the sliding arm, though honestly, threading the hole directly in the plywood would have worked too. To prevent the screw tip from chewing up the wood, I added a small steel tongue cut from sheet metal to take the pressure. Now the mount is ready for the upper blade guide. At least now there is a proper place to attach it. For convenience, I should really make a small hand wheel for adjustments, but for now a wrench will do. I will add the hand wheels later, after field testing. Here's my collection of bearings, most long past their prime. Still, a few are usable, perfect for this job. Next comes choosing the guide configuration. There are plenty of designs, but first you need to decide how the thrust bearing will contact the blade's back edge against the end face of the outer race's side. I went with the latter. The bearing's shaft will be a simple M10 bolt, threaded directly into the plywood arm. To make the blade's spine contact the bearing's center line, I glued on a small piece of laminate. Then trim the excess neatly. I could just screw the bearing block directly to the arm, but since I'll be using blades of different width, their back edges will contact the bearings at different spots, so it makes sense to include horizontal adjustment, meaning slots, instead of fixed holes for the mounting bolts. You could do it with a handheld router and a pair of stops, but I've got a small jet benchtop metal mill, so I use that instead. After all, you could make the slot with a chisel, but when there is a right tool at hand, it's a sin not to give the screw head a proper seat by cutting a small recess for it. With that, the blade stop is ready. Now it's time to make the slide guides, the parts that will keep the blade steady. This is where a bandsaw would have been especially handy. Cutting small pieces on it is so much more convenient. Through trials and error, I've learned that the best guides are the ones that press against the blade at about 45 degrees. Wooden blocks would do fine. However, I still have some fluoroplastic stock left. Fluoroplastic polymer slides over steel more easily, and I decided to use it. To hold the blocks in place, I made small shaped washers from stainless steel. I will admit, I cut the first one off the strip too early, rushed a bit. It's easier to drill holes, round the edges, and polish the surface when you're working on a longer piece. It gives you something to hold on to. Learn from mistakes. I marked the screw holes by tapping directly over the spot with the hammer. Then I cut an M8 thread right into the plywood. In my opinion, the stabilizer module turned out quite solid. The saw blade will be held between these white fluoroplastic blocks. When they wear down, I will just loosen the screws and move the blocks closer to the blade. Next, I fastened the whole assembly to the movable support arm. The final adjustment, a few taps with a hammer and a clamp to hold it in place. At this point, the saw blade is not yet set correctly. When idle, it shouldn't touch the thrust bearing at all. Now, I need to make the lower stationary stabilizer for the saw blade, but just for the variety, I will make this one experimental, using the simplest design possible. For that, I took a triangular piece of a graphite-filled caprolon, trimmed the edges, and fastened it to an oak base with screws. Then I needed to mark where to cut a groove for the saw blade. If you press the caprolon block against the back of the blade and briefly power the motor, the blade will leave a fine mark. Following that mark, you can make a precise cut in the caprolon block, exactly where the saw blade runs. Then you just screw the block into place, tilt the saw on its side, and you're ready for the first test cut. As you can see, I connected two rolling cabinets with a sheet of plywood to make a makeshift sled and mounted a dry birch log on it. At first I was cautious, but then gained confidence and sped up. The saw easily cut through 12 cm 5" of dry birch. On the second cut, I started to deal with the sawdust sticking to the pulley. My old brush didn't perform well, but the resulting board turned out decent, ready for planing and gluing. While cutting the second board, I noticed a rhythmic sound, a sign that the saw wasn't cutting evenly. Watching the upper guide more closely, I noticed the back of the blade wobble. That shouldn't happen. I'm sure you can hear that knocking sound too. After a few more cuts, the knock grew louder under load and quieted when idling. It matched each full rotation of the blade, and as the cut widened, the sled began to shake in rhyme with it. That led me to suspect the blade itself. And after just a few cuts, the upper stabilizer needed readjustment. The blade started to climb upward during the cut. I had to stop and reset it. It became clear I needed to test what the machine was truly capable of, how large a log it could realistically handle. With the 35 cm 14" birch stump, the saw managed, but only barely. The test showed that the brush against the blade was unnecessary. It's better to sweep sawdust directly off the pulley face. A simple toothbrush and two screws did the trick. I also checked the caprolon block for wear, and to my surprise, there was none at all. I had expected it to gradually polish itself against the blade, reducing friction, but that didn't happen. Large chips on the floor don't bother me much, but since I work indoors, I needed to deal with the fine dust. I made a hose adapter for my cyclone from a plastic bottle, and the small dust is now pulled into my homemade extractor, a tin bucket connected with 2 PVC elbows. That simple setup is 8 years old and it hasn't gone out of date. After leveling the blade properly, the saw stopped drifting upward, and the oak cuts came out clean and straight. Considering that the wood had been drying for 6 years, those boards will stay flat and true. By this point, I realized I'd eventually have to resharpen the blade in my own way, but decided to wait until it naturally dulled. It always feels wrong to grind a brand new blade. For now, I just need to gain more experience cutting logs into boards. You can clearly see the difference in surface texture between cuts made with the chainsaw and with the bandsaw. In terms of flatness, the difference isn't dramatic, but in smoothness, the bandsaw is miles ahead. Cutting thin lamellas with the chainsaw makes no sense. Most of the wood turns into dust. After trimming the log on the bandsaw, I decided to try slicing a thin lamella just to see what would happen. Here you can see a close-up of the blade cutting as I push the sled forward. It shows clearly how straightforward this kind of work is. Anyone could handle it. The cyclone catches only the fine dust, while larger chips fly away. In the upper left corner, you can see a quick tensioning rig, a simple bolt with a bearing, mounted on a board and held by a clamp. That was needed because the belt had sagged and started slipping on the pulleys, because the blade had dulled. There's no point sawing with a tired blade. A good tool must be sharp. It's better to resharpen an already sharp one than to suffer through the cut with a dull blade. Still, this was a test, so I decided to make one less board to confirm it. That broke my own rule, but the test had to be finished. And with that, the prototype trials were complete. I was using a 1.1mm thick blade driven by a 3-phase 1.1 kilowatt motor wired in a delta configuration through a stud capacitor, meaning it ran at roughly 70% of its rated power. For this blade thickness, that power clearly wasn't enough. At minimum, a frequency diverter was needed. Here is the wiring diagram, simple and open for anyone to use. While I was at it, I trued the pulley and removed the wobble. Few vibrations, a small victory in the eternal war against vibration. And here's a comparison. The fine dust inside the cyclone's bin versus the coarse chips on the floor. They each tell their own story. Now it was time for a little experiment. Hand sharpening a bandsaw blade. To begin, I decided to refresh just the front edge of each tooth. For that, I used a piece from a chainsaw sharpener. Why not? Nobody else seems to do it, but I'm not breaking any physics laws. By resting the sharpener's body against the back of the sawtooth, it's easy to keep a 90-degree reference and a consistent cutting angle. To show the process properly, I even bought a small microscope. This is what a freshly sharpened tooth looks like. And here, a tooth that has just been cleaned, barely dulled at all. The difference is subtle. But here is one with clear view. You can see the scuff marks, even signs of plastic deformation. Notice the tiny burr curling over the back edge of the tooth? Most likely that came from a bad sharpening. One I did intentionally, pressing too hard and overheating the edge. See how the metal turned color, the edge curling and showing heat marks on the flank? And here is a tooth cleaned of pitch, one that should have been sharpened long ago. Compare it to the newly sharpened one, and you will see that the teeth wear very unevenly. You probably guessed already. The worn and unworn teeth sit opposite of each other on the same loop of blade, like opposite poles. And there it was, the real cause of uneven wear and the rhythmic knocking sound. The cause of the jerky feed that shakes the sled and roughens the surface of the board. The blade, welded from a saw strip, had been joined crookedly. Watch closely. The back of the blade wobbles 2 mm back and forth. Most teeth never actually cut, while the ones that stick out further take all the load. So I had been cutting the whole time with the bad blade. Disappointing? Yes, but all the more credit to the homemade saw for putting up with it. Still, to understand what each change really does, I would need to keep using this imperfect blade a little longer. From the earlier project, the one about milling oak slabs with a chainsaw, I still had plenty of dry, seasoned material. Once cut into boards, it all goes into my benches, stands, and cabinets for the workshop. Too bad it had to be milled while fighting against a stubborn blade. At least now I know using a poorly welded bandsaw blade is simply not worth it. Lesson learned. But that's the whole point. You watch so you don't repeat my mistakes. Along the way, I noticed something else. The frequency inverter, judging by feel, added about 10% more cutting speed. And you may have noticed by this stage, the crooked blade was making the sled shake much harder than it did at the start. Soon, that observation would lead me to flip the blade inside out and cut in reverse, but that comes later. First, I needed to straighten the crooked blade as best as I could. Ideally, you would cut it apart and weld it properly again, but I didn't have the setup for that. What I did have was an angle grinder, a couple of wooden blocks, and some tape, enough to polish the edges of the loop and even them out. Except for one small issue. The sparks were flying straight towards the frequency drive. Not a great idea. So I unscrewed two fasteners and temporarily hung the inverter from the ceiling with a clamp, well out of the harm's way. No one online seemed to have tried straightening a blade this way. How do you think it turned out? Exactly. It turned out into a surprisingly time-consuming experiment. After 15 minutes, the spark zone wasn't any longer. I even switched from the grinder to a bench sharpener with a diamond cup wheel, and that only made things worse. After 20 minutes, though, progress became visible. The spark trail grew longer. By then, my hands were tired from holding the grinder, so I rigged up a crude auto feed and went off to have some tea. When I returned, the sparks were streaming continuously, a good sign that I had finally ground down the main high spot, but the micrometer still showed a shallow dip, 0.2 of a millimeter deep. The grinder was hot, so I swapped it for a smaller one. To remove the final bit, I had to reduce pressure to a minimum. Too much pressure and the blade would flex away from the wheel. Now, during cutting, the blade pressed against the bearing would no longer wander on the pulley. All that was left was to level the teeth. Here, the metal to remove was 100 times less, and the work took only a few minutes, longer to set up the camera than to finish the job. The weld seam was exactly where the high spot had been, so I had to be careful not to overdo it. You can't go by the sparks here. The moment you just touch the cutting edge of the last tooth, there won't be any. That's when you stop. I almost managed it perfectly. Here's a side-by-side comparison, the worn-out blade and the freshly trued one. Obviously, you can't cut with it yet. The tooth face now runs parallel to the back edge, so it won't bite into wood. Like with the drill bit, it needs clearance behind the edge. There is a catch though. A saw blade has set. Every third tooth is neutral, while the neighbors are bent left and right. Factory sharpeners don't compensate for that, but since I sharpen by hand, I can. I control material removal by watching the light reflection. Now I'm forming the back edge of each tooth, taking the set into account. My sharpening angle is about 100 degrees, not 90, much like a circular saw. The grinder's pendulum rest keeps the angle steady. It is quiet, rhythmic work, almost meditative. My thoughts wander while my hands move automatically. To avoid losing track of which teeth I've done, I mark them with a permanent pen. Sharpening is a vast subject, too big to cover here, so let's move to the results. After correcting the geometry and regrinding the teeth, the saw cut more aggressively than even a new one, with a slightly narrower curve. But the jolts and the sled's side shakes didn't disappear. There are two possible reasons. When the two ends of the blade were welded not exactly at 180 degrees, the bend formed a triangulated cone instead of a perfect cylinder. Straightening the edges makes them even, but the figure-8 twist remains. Also, where the teeth were ground more heavily, the overall width narrowed because of reduced set. Which cause mattered more doesn't really matter. It was time to test another idea. replacing the fixed guides with rolling bearings, like those used on real sawmill blades. I wanted to see how the two systems compared under the same conditions. I didn't bother machining my own rollers, just bought them. To mount one, I drilled holes through the block and the board, inserted the rolled shaft and fixed everything with 2 screws. Simple as it can be. It is a temporary setup, so it's rough and quick. Once I test it properly, I will rebuild it with the lessons learned. For now, a few screws and a clamp are enough. By this stage, my makeshift sled had loosened up, so I began thinking about upgrading it. But first, I needed to test the roller. It is noisier than the wooden guide, but it works, and adjusting it is easy. A single quick release clamp sets the roller depth in seconds. Next, I decided to try 2 rollers side by side. The 2 rolling cabinets were still connected by plywood strips, held with just 3 screws each. Clearly not enough. I added another plywood brace on the side, lifted it a bit, and added more screws. On that raised section, I mounted 3 furniture dolly rollers, the same kind I use under my long workbench. The bench's side panel serves as a vertical track, letting the sled move smoothly along it. Now, if you flip the blade inside out and cut in reverse, the saw actually presses the sled toward the bench. The side rollers engage, and any sideways movement becomes impossible. The bench itself keeps the sled from shifting left. Sure, you can cut by pushing the sled diagonally, holding it tight to the bench, but it is far more efficient to simply flip the blade. The 1.1mm blade is fairly stiff, and mine is short, just 3.2 meters long, so turning it inside out takes real effort, so you have to be careful not to hurt yourself. Up to this point, I'd been sawing with a 1.1 kilowatt motor. Now it was time to replace it with the one twice as powerful. That meant disassembling the saw and showing you how it's built along the way. As you can see, the frame simply rested on the bench and an anvil, held to metal support by a single clamp. And that's the beautiful wooden design. I bought the new motor with the pulley already installed. For compactness, however, it made sense to flip the pulley with the groove facing inward. To press it out, I used a simple carpentry trick, a set of wooden wedges. And of course, what workshop task is ever complete without a file? The motor is noticeably heavier and bulkier. With the stock cover on, it wouldn't fit into the Bandsaw frame. No problem, the cover can easily be replaced with a piece of Textolite. Here's enough space to tuck the wires neatly under it. Here's a small tip. The jaws of a lathe chuck have grooves that perfectly fit the heads of furniture bolts. You can use them to turn down the threaded section of any size you need. Very handy. To mount the new, larger motor, I needed new holes. The old platform didn't have any room left, so I turned a dowel, glued it into an unused hole, and freed up space for the new bolts. That saved me from cutting a fresh piece of plywood. Once the wires were cleaned and tinned, the motor could be connected to the existing frequency converter, conveniently rated for 2.2 kilowatts. The test fit went well. After fine-tuning pulley alignment, I could finally return the saw to the anvil and the workbench. Doing all this alone feels like trying to base a hippopotamus. Not impossible, but certainly not graceful. You might think I just needed an extra pair of hands, but in truth, what I really lacked was a drop of oil for the thinking lamp. I thought it would be difficult to mount the motor horizontally on the frame fixed to the anvil, so I decided to try attaching it to the rolling base first, built from stacked KLT boxes. What I didn't account for was how heavy the motor actually was. It overbalanced everything. A perfect reminder that persistence isn't always a virtue. Sometimes it's wiser to accept reality and abandon a bad idea. I should have mounted the motor separately from the start. And while you watch me wrestle with my own stubbornness, here's a quick favor to ask. You know what really helps small channels survive the algorithms? your likes, comments, and especially reposts. Sharing a video helps far more than you might think, and thank you. Meanwhile, from a scrap of plastic, a leftover base of a 5-liter bottle, I made a washer to keep the pulley from sliding off the motor shaft. Waste not, want not. The plywood spring of the tensioner works fine overall, except that the plywood doesn't slide well against itself. With the bandsaw blade fully tensioned, friction in the plywood spring made the tilt adjustment stiff, so I decided to cut a sliding spacer from graphite-filled Caprolon. Here it is. I just needed to drill a hole for the tensioning bolt. While we are at the topic of tensioner and wheel tilt, I will admit, I grew tired of turning nuts with the wrench each time I adjusted the blade tension or tilt. It is awkward and slow. Among my scraps, I had several round cutouts from laminated plywood, leftovers from using a hole saw, perfect for making small hand wheels. One for the tensioner, a bit larger, another for tilt adjustment. They should be comfortable for grip, yet large enough to give decent leverage. To make them pleasant to hold, I rounded the edges. On a lathe, that's a 5-minute job. A bit of sanding and a coat of wax brought a soft sheen and keeps them from getting grimy too quickly. Quick work, but neat. Each hand wheel should press against the bearing. If you don't have a thrust bearing on hand, and I didn't, you can make a simple housing from a washer of suitable diameter. Using new bearings here feels wasteful. As you can see, with the Caprolon spacer installed, both the tensioner and tilt mechanism now work much more smoothly. And the forces involved are no joke. You can tell from the stripped threads on the tension rod. Naturally, for comparison, I installed a second roller in place of the last remaining guide block. The roller was store-bought, but it is slightly off-center. Once pressed in, the bearing spun with jerks. Not ideal, but it will do for now. All my projects are connected by a running storyline. You might recall in last year's video about the DIY miter saw system, I split a birch log and cut out a block from it. Many viewers asked why. Well, here's the answer. I've planed the same block and now it's ready to be used. Recognize it? I'm drilling that very same piece now. In case you want to see the original video, it is linked below. My Benchmade Forstner bit cuts surprisingly cleanly. I need to drill 2 holes of different diameters in the board and 1 hole in the block, same as the last time. The test board can be shortened for compactness. As you can see, my long workbench holds 2 saws at once, a bandsaw and a circular saw. In theory, I could cut stock in 2 planes simultaneously. The birch block with 2 holes will be halved. Both pieces will find use, but first it's best to mark the cut directly on the setup. With the saw fixed to the bench, it's a 10-second job. I hadn't yet tried cutting dry aspen on this saw. You might remember from the video 2 Secrets of Chainsaw Milling that I had already prepared a half log of that very wood. That was a long time ago. Since then, the aspen has dried beautifully, perfect for testing. Freshly cut, the wood was damp and the cut surface smooth. Years later, the board was warped, a reminder that only pre-dried wood keeps its shape. It's almost impossible to dry a full log without cracks. I do have a project for an innovative log drying method, but it doesn't work for wind-fallen wood, so that experiment has stretched into years. These boards are from wind-fallen aspen. They spent the winter buried in snow, which gave them a grayish tint. Fresh aspen is bright white, but since I'm making beehive frames, color isn't important. At this point, I got briefly distracted. I was out catching a swarm, and the bees gave me a little sting therapy in the left hand. As you can see, these modular rolling cabinets are incredibly handy in the workshop. I store tools in them, use them as low assembly tables, or pair them up as a rolling base for log cutting. Each KLT box module serves as a workbench, a perforated top, a storage unit, even the base for my miter saw. In a small hobby shop, everything should serve more than one purpose. After reversing the saw blade, I noticed an important change. During the cut, the blade now presses the log firmly against the long bench. The jerks and vibrations disappeared. Even though the resharpened blade cuts more aggressively, the rollers now do their job, keeping the carriage steady. I'm cutting green wood now, expecting smoother work than with dry stock. I thought there would be less airborne dust, yet even before the cyclone handled the fine dust well, while coarse chips fell straight to the bench. Watching the blade and chips, you can clearly see the small rhythmic jumps, the result of uneven material removal. The blade should ride freely between the rollers, centered naturally by the crowned wheel. When it doesn't, the blade oscillates back and forth, creating those jerks. The only real fix was to replace the blade entirely. By the way, take a look at this birch grain, Patchouli vulgaris. In a shade I like to call pomegranate purple, though some would say blood crimson. After drying, planing, and a coat of oil, the pattern will stand out even more vividly. Right now, the raised fibers from the saw mask much of the beauty. I usually wedge logs tightly between the carriage walls. It's secure and doesn't mar the wood like screws would. It's never failed me once. Now it's time to mill a real log, something over 2 meters long. The shop could technically fit up to 3.5 meters, 12 feet, but such logs are awkward to maneuver. I adjust the cutting height with spacers under the log. To remove the first slab, I take all the spacers out. In this case, a 120mm beam. With a little thought, even a large log can be moved with minimal effort. As they say, drag what's flat, roll what's round. After the first cut, I roll the log and lay it flat on its newly sawn base. Take a look. See how the blade walks about 10mm back and forth across the roller? That's our cue to test another blade. This one is narrower, 35mm, 1.4 inches wide, and arrived coiled awkwardly. Even after 2 weeks lying flat, it never straightened completely. Apparently, I still haven't managed to buy a properly made saw blade. I may have to learn to weld them myself. Despite full tension, the blade remains slightly twisted. Naturally, that wreaks havoc on the curve width. Over-tightening the tensioner isn't an option either. It stresses the bearings and shortens the blade life. But experiments must go on, so I'll work with what I have. Once buried in the cut, the blade steadies a bit, though the curve remains wider than before. Still, this new blade cuts smoothly, no jerks. After all the struggle, that alone feels like a triumph. On full-scale sawmills, operators spray the blade with soapy water in summer or diesel fuel in winter, not as lubrication but for cooling. I don't need that here. My motor is modest and my blade cools itself when idle. Now I will test this blade on dry oak, pushing for maximum cutting width. True, my roller tensioners are fixed a bit off, reducing the available cut width, so I'll trim the board slightly. For that, an electric chainsaw works perfectly. Looking at the grain on the log's end, I decided to cut the plank for mostly radial boards. Since I'll be cutting it on edge, I could have skipped trimming the slab, but it's easier to rest the stock on a flat, perpendicular surface than to fuss with shims. In short, a chainsaw near the mill is indispensable, especially in a case like this, when the log's butt simply won't fit through the cellar door. The base cut near the roots, full of grain twists, reveals a beautiful grain pattern, once planed, too lovely for firewood. When you compare a rough chainsaw cut to one made on a bandsaw, the difference is clear. The bandsaw delivers a much cleaner and more precise surface. At one point, I experimented with using WD-40 as a lubricant for the saw blade. It didn't help the cut in any way, but during the process I noticed the rubber ring on the vibration damper had turned sticky. Since it wasn't glued in place, I simply flipped it over. While inspecting the saw, I also noticed the blade occasionally touching the rim of the wheel at its outermost position. I ground that rim down using a handheld belt sander. This particular wood cut was heavily twisted in grain, hard to split along the fibers. That kind of wood is perfect for tool handles, so I set it aside for the next batch of handmade axes and hammers. Then came the moment to regrind the blade, this time using a new approach. In blade sharpening, consistency of movement is everything. To make hand sharpening more repeatable, I modified my grinding setup slightly, trimmed off the unnecessary parts, and added a shaped stop washer. By pressing each saw tooth firmly into the washer slot, I grind down every fifth tooth ahead until the abrasive wheel no longer removes material. This ensures all right hand teeth end up with the same height and angle. The right teeth were simple enough, but to sharpen the left ones the same way, I would have had to flip the whole blade. Instead, I decided to install a small stop screw inside the housing. That's when I accidentally cracked the diamond grinding wheel. I won't lie, that hurt. They're not easy to find. So I decided to save what's left of the diamond wheel and continue using a regular disc made for chainsaw sharpening instead. Like before, I'm using a slightly unorthodox method for bandsaw blades. This time though, I'm sharpening along the front face of the tooth, which is technically the correct side. For now, the head of the stop screw simply rests against the tooth, setting the sharpening angle but not the depth of cut. The difference between the curve before and after sharpening is visible, though not easy to show clearly on video. If you look closely, you might notice the transition from a wider curve to a narrower one. The saw cut has become thinner, perhaps because of sharper teeth, or maybe due to slight offset in the sharpening pattern. At the bottom of the frame, you can even see a small step where the newly sharpened blade transitions to the older, duller one. A few words about blade tension. I don't believe in over-tightening. It only shortens the blade's lifespan and adds strain to the bearings. I tension the blade just until it rings a clean C note when plucked. If you prefer more precision, you can use a tuning app. It works perfectly. More importantly, watch this. There isn't enough depth of field on camera, but on your own saw, observe how real misalignment can bend the blade into a shallow arc. I suspect that's best avoided, though I don't yet have enough experience to say for sure. It is possible that a slightly arched blade, meeting the log belly first, could compensate for the downward flex that occurs during cutting and reduce fatigue cracks near the blade's spine. So far, I've sawn only a couple of cubic meters of boards with this setup, not nearly enough experience to draw firm conclusions. To speak with authority, one should need a full-scale sawmill, dozens of worn-out blades, and years of testing. That's still ahead of me. I know that most people buy properly made straight bandsaw blades. Mine are 1.1 mm thick, but I have heard 0.8 mm blades perform better. Blade thickness really matters. According to the standards of the last century, a 1 mm thick blade should be run on wheels at least 1 meter in diameter, not 40 centimeters like on my setup. Only then will it last through dozens of sharpenings. The curve width also matters. It affects both cutting speed and wood waste. After using a chainsaw to mill lumber for years, these sawdust losses may seem tiny to me. But once you start comparing, you realize how much every millimeter counts. Over the past year, I have sawn far more wood than what was shown in my videos, and I have spent countless hours refining the process. Naturally, I now feel an almost burning desire to cut logs into boards faster. A thinner 0.1 mm blade promises exactly that. Filming and editing the full process at that scale would be excessive, and mass-producing content for its own sake isn't really my style. Friends, thank you sincerely for your support on Patreon. Without you, the video simply wouldn't have happened. I truly consider you co-authors of this project. Now, a small warning. I'm about to push the blade slightly past its limit, and it's going to slice straight through my vacuum hose. I really should design a more efficient chip collector. While the dust doesn't fly everywhere, the shavings pile up quickly, far too quickly. Any advice on improving dust extraction would be much appreciated. With the current setup, the maximum log diameter I can mill is about 55 centimeters, 2 feet. That's determined by the layout of the tensioning rollers. But to saw anything that size, I will need to work outdoors. The logs simply won't fit through the basement door. For comparison, here's my first bandsaw. A complete disappointment. I did manage to learn how to sharpen its blades so they cut straight and true, but they only lasted a few minutes before snapping. Wasteful and frustrating. I strongly advise against small wheel bandsaws. All my efforts to reinforce the frame were wasted. That machine was junk. You may recall though that it served as a prototype for a traditional style bandsaw meant for thin, fine blades, not full-scale sawmill work. This current video, however, is mainly about the concept of the new composite frame and demonstrating its potential. Since I can't swing a full log inside the basement, let's head outdoors. Things are about to get interesting. This little blacksmith's hammer is too light for the next test. Let's bring out something heavier. Go ahead, pause the video and place your bets, folks. I claim that under the sledgehammer, a cast iron bandsaw frame will crack, a steel one will bend, and my composite frame won't even flinch. I can already hear the skeptics, but I have a load testing setup and a 12-ton dynamometer. Anyone who wants to test this claim in practice is welcome to bring their own cast iron or steel bandsaw. We will apply impact loads until the first one fails. Of course, a piece of railway track would be stronger, but the machines must be of comparable scale to keep it fair. And before we wrap up, a quick word of caution. Be careful and take care of your health. This bandsaw has already claimed a bit of my blood. Since the tensioner and tilt mechanisms weren't clearly visible indoors, I'll show them now in their proper vertical position. This was Max Igorov, and thank you for your likes, comments and reposts. And may good people watch good videos. I hope to see you back on Advoko Makes.